I need to understand about plasma physics and all that. But in the meantime, I'll tell you a little bit about what I know. And I'm afraid I'm not going to mention the magnetic field, so please bear with me with that. But there will be plenty of turbulence here. So and the idea is that the organizers asked me to talk about our recent comparison on about two models for molecular clouds and their star formation activity. One of them is the model of turbulent support, which has been around for maybe, I don't know, 25 years, 30 years now. And well, actually, its origins are 50 years old, but the model regained strength at the turn of the century. But now we're advocating for the possibility that molecular clouds are in fact not supported and rather undergoing at least partial global hierarchical collapse motions. And that's what I would like to talk about. And so, okay. So this is the list of my collaborators, which of course I don't have time to read, but they have all participated actively with ideas at least. And what I would like to talk to you about is first, since especially not everybody here is a molecular cloud aficionado, I would like to review some of the properties of the molecular clouds and their star formation activity that we would like to address and understand from models for them. And then I would like to go into, got the wrong button, to go into how each one of the models interprets these properties, and that's very important. That's the fundamental idea of this talk. To see how we think about the things we observe and simulate in our computers. And then if I have time, I would like to go a little bit on how the models seem to be converging or onto what are they converging and some tests that we could perform to understand and to somehow come to an agreement. So what are the properties of the molecular clouds that we would like to understand? First is, I would like to really emphasize this. I learned this when I was in grad school, but I don't seem to hear it mentioned anywhere in recent times. And that is the fact that they contain a huge number of gene masses. For molecular gas, for example, again, wrong button. For molecular gas at about 100 particles per cubic centimeter and 10 K of temperature, the gene mass is about 45 solar masses. But molecular clouds contain thousands or even up to 1 million solar masses. So they contain huge number of gene masses. So a 10 to the 4 solar mass cloud contains about 200 gene masses. So they have a strong tendency to collapse. Now, second item, their internal structure. And this was, I think, at least to my knowledge, first pointed out by Edith precisely and by Michel in a paper in 1992, where they emphasized that with the data available at those times, the clouds had substructure down to where the resolution allowed them to see. So basically, they just had like 3 levels of hierarchical observations and showing that there was substructure at every level. Probably that was simultaneous with Edith's thinking of clouds in terms of fractals. And so the modern version or interpretation of that is that molecular clouds contain filamentary structure that we today call hub filament systems that consist of a roundish hub, typical sizes of about 1 parsec that are surrounded and most likely fed by filaments that extend for several parsecs. And along these filaments, there are also cores, which are like smaller versions of these guys. And I have the total impression that these guys contain small-scale replications of the large-scale structure. So I would think that this structure is repeated at multiple scales. And just today, we saw a system that reminded me very much of this picture, but at the kiloparsec scale. So third property is that they are characterized by scaling relations and that are related to their energy budget. So the scaling relations have been already mentioned in the meeting by Eva, and those were discovered by Richard Larson in 1981, and they are basically 2 relationships with 1 consequence, 1 third relation, which is a consequence of the other 2. the two relations are one between the velocity dispersion and the size, and the other is between the density and the size. And like Larson first presented them, was that except in its more modern version with the more recently determined value of the exponent, is that the velocity dispersion scales like the size of the clouds to the 1/2 power. And this is typically interpreted as the signature of compressible turbulence with the Berger spectrum. And this is what I was mentioning the other day to Bill, that we somehow translate the Berger spectrum into a size velocity dispersion relation, which I'm not totally convinced that is valid. Second is the density size relation that tells us that the density scales like the size to the -1 power. And this particular property implies that the column density, which to 0th order approximation is obtained by multiplying the volume density by the length of the object, so that you get the total amount of matter along your line of sight, is about constant. And then, or alternatively, these days it is common to speak about the mass-size relation, and in this case, the mass would go like the size squared. Continuing with this, the third Larson relation is that the two previous ones, including their normalizations or their actual factors, imply that the clouds are in rough equilibrium between their kinetic and magnetic energies. So Larson himself plotted this quantity, which is essentially the ratio of the gravitational energy over twice the kinetic energy, and he showed that this was roughly independent of the size scale. And now it's interesting to note that this is essentially 1 over the quantity that we currently call the virial parameter, which is twice the kinetic energy divided by the gravitational energy. So saying that the clouds appear to be in rough equipartition between gravity and kinetic energy. And I specifically don't want to say turbulence. So this energy budget is also measured using the Kito-Heyer diagram that also Eva introduced in her talk, in which we plot the so-called Larson ratio, which is the velocity dispersion divided by size to the 1/2 power, which according to Larson's velocity dispersion size relation should remain constant. We plotted it against the column density, and he showed for a sample of clouds that were not anymore restricted to having constant column density, that he showed that this ratio scales like the square root of the column density. And this is exactly what you expect from equipartition again. So you could say that yes, the equipartition remains, but that the column density is not really necessarily a constant. And this is essentially just a selection criterion derived from the way we used to define molecular clouds at the beginning. But the rough energy equipartition remains. More recent data actually indicate that there's no precise equipartition across all the entire mass range, but instead more massive objects of a given kind seem to be more strongly bound. And this is, again, the virial parameter, so the ratio of kinetic to gravitational energy, plotted against the mass, and we see that it is the most massive molecular clouds that are close to this equipartition value. And this is also shown here in the Kito-Heyer plot, where we plot this Larson ratio against the column density. And in fact, this extends to objects that are denser than molecular clouds, to, for example, massive clumps, which have sizes of about a parsec, but very large masses on the order of 10 to the 3. And we see that the scaling continues, but now these guys are apparently very strongly bound. They have lower kinetic energies than their gravitational energies. Okay, so that's for the scaling relations. And now, the fourth property that I would like to emphasize is the inefficiency of star formation. And this is the problem that has been around for 50 years. Zuckerman and Palmer in 1974, in their annual reviews paper, they showed or argued that the star formation rate is much lower than its theoretical maximum, and this maximum would be given by taking just the total molecular mass in the galaxy and dividing it by the mean free fall time of the gas. And that would give you an estimate of about 300 solar masses per year, which is about 100 times larger than the actual observed value. The other problem that they pointed out, and this is not so frequently mentioned, is that at the time there were no systematic velocity difference observed between the outer parts of the clouds and the inner parts that would be measured by redshifts between the two. And so this second property in particular led them to suggest that the line widths, instead of corresponding to freefall motions, corresponded to supersonic but microscopic turbulence, so meaning it was confined to scales much smaller than the cloud, in order to avoid seeing velocity gradients that should have been observed at the time. However, I don't think that this lack of observation holds today. Today there are several pieces of evidence that show the gradients, large-scale gradients along molecular clouds. So, but what Zuckerman and Evans were requiring essentially was that the turbulence constituted a sort of additional temperature that would provide a pressure to hold the clouds up against their weight. Either that or magnetic support. Okay, I mentioned the magnetic field once, but that's the only time I'll mention it. But I won't mention it because now it's known that the magnetic energy is in general insufficient in molecular gas to support the weight. So it has other or second order effects in my point of view, but unfortunately I don't have time to talk about it. So many of these ideas persist today. In particular, the interpretation that the velocity dispersion corresponds exclusively to turbulence and that this turbulence provides support. This, no matter what paper you read, that's the interpretation of the velocity dispersion and then of the associated virial parameter, which is interpreted as a measure of support. So this persists today, no matter what simulation or observation you look at. Okay, so now for how the two models interpret the observations and these properties of the clouds. And again, like I said, I want to emphasize the role of of the conceptual models, the ones that I just discussed, and how perhaps how they are analytically formulated. Not so much the numerical simulations, which may contain signatures of one type or the other, but it really strongly depends on how we interpret them. And I'm pointing this out because this has been a matter of discussion with the referee. Anyway, so what are the turbulent support model premises? And first, molecular clouds are prevented from gravitational contraction by supersonic turbulence, which in general balances, to explain this approximate equipartition, or perhaps exceeds, exceeds the gravitational energy so that the virial parameter is of the order or larger than unity. And so the interpretation is that the clouds are in near virial equilibrium between turbulence and gravity, or even supervirial, so that they could be either dispersing, or in some cases there have been models that try to confine them with external pressure. Second is that the masses of the clouds are given by the distribution of masses of the turbulent density fluctuations in the kind of models that, for example, Patrick discussed the other day. Third is the Larson velocity dispersion size relation is a signature, a manifestation of the supersonic turbulence in the medium, for which the Berger spectrum, which has a form of k to the minus 2, applies. So this spectrum, when you translate it to a velocity dispersion relation, would imply the Larson scaling relation. Fourth is that the supersonic turbulence within the clouds produces post-shock density fluctuations, which constitute the substructures of the clouds. So you have clumps, filaments, cores, and they are all in these three scales or subscales in the clouds, they are assumed to be turbulent density fluctuations. And so the cores in particular are the one type of structures that the initial theories or models among which I count myself 22 years ago, would say that those structures are the ones that finally can go into collapse and then begin to form stars. And the interpretation for the low efficiency of star formation was that only these tiny regions in the clouds would go into collapse, the rest of the cloud being supported by the turbulence. A more recent impersonation of this model is the inertial inflow model by Perrault and et al. That suggests that the hot filament systems that I mentioned before are produced by inertial inflow, meaning non-gravitational inflow on scales of 1 to 10 parsecs, for example. And they, in fact, drew this scheme of how the compressions would operate. But note that this is a very concentrated compression that would, I think, be highly unlikely in real turbulence, especially in supersonic turbulence that would be dominated by shock passing. And this suggestion was based on the argument that, as they said, on that scale, on this scale here, usually the turbulent energy exceeds both the thermal and the gravitational energies. But note that this is actually perhaps not all that consistent with what we saw before, that the most massive regions tend to be the most strongly bound. And these objects are known to be among the massive parts, the massive subregions of molecular clouds. I'll come back to this later. Okay, no, there's more. Now, because the clouds are in equilibrium, okay, that's the fundamental assumptions, that the clouds are not collapsing. Then the velocity dispersion corresponds exclusively to supporting turbulence. And moreover, because they're in equilibrium, since they're just standing there, there's no specific theoretical prediction for how should the clouds evolve. And therefore, in models for control of the star formation rate, the star formation rate is essentially governed by the parameters of the turbulence, which is somehow externally applied, either by cascading from the larger scales or either by supernova driving or H2 region driving. And the parameters are then the virial parameter, the sonic and Mach Mach numbers, and the compressibility of the turbulence. And Christophe Federath and Ralf Klessen have an excellent summary of how all these models work together and how you can understand them. And then, so what's to be concluded here is that the main controlling parameters of the star formation rate are the properties of the turbulence. Mm-hmm. Now, let's switch to the GHC, the Global Hierarchical Collapse model premises. And I would like to emphasize that this is a strictly evolutionary scenario. Mm-hmm. So, first, since it's evolutionary, we want to understand how do the molecular clouds form in the first place. And of course, you can think that supernovae are just shuffling up around the molecular gas, but in principle, you want to understand how the molecular gas formed in the first place. And there, the obvious source or the obvious first step is the atomic gas. And so the idea is that the molecular clouds form from compressions in the WNM, in the warm neutral gas, where that lead to phase transitions through the thermal instability to form cold neutral medium clouds. And then the important part is that this transition, because it is to a denser and colder gas by factors of 100 each, keeping the pressure constant, that implies that the G's mass drops by a factor of 10 to the 4. So it's a gigantic amount in the jump of the G's mass. It drops dramatically. So that gives you a perfect prescription for forming strongly gravity-dominated gas. Mm-hmm. Second is that the turbulence in the clouds is not as strong, the real turbulence in the clouds is not as strong as we have thought it to be. Typically we quote as a rule of thumb that the Mach number in clouds is about 10. The sonic Mach number is about 10. But we would like to argue that instead of being of the order of 10, it is on the order of a few. And this was already mentioned by Marc-Antoine in his talk, that this is basically the type of Mach numbers that we see in these when we simulate the formation of the cloud. So let me present this simulation again. This is an old simulation, almost 20 years old, but this is what led us to realize. I was precisely looking for the origin of the turbulence in the clouds, and I thought that precisely it would be something that could be unavoidable was the turbulence generated by the formation, the assembly mechanism of the cloud itself. That's unavoidable. That doesn't depend on whether you have stars around or whatever. If you form a cloud, you generate turbulence. Is that turbulence enough to support the clouds? Well, it turned out that it doesn't. The cloud underwent this evolution. It formed, right? So this is a plot of the gravitational, kinetic, and thermal energies of the cloud, of the dense gas. And you can see that at the beginning, you only have the thermal energy, the kinetic energy, and the kinetic energy is somewhat larger, by a factor of a few 10, perhaps a factor of 2, larger than the thermal energy, but not much by that. And then there's no gravity here. The gravity is not important at all yet. But once the gravity becomes important, the gravitational energy becomes important, then it began dragging the kinetic energy along with it. But now this is not turbulence, this is inflow. So so our claim is that there's a significant, perhaps dominant amount of inflow motions in the kinetic energy of the cloud. So one of the take-home messages is that we need to distinguish between inflow and turbulence. Yes?
How resolved is the internal structure of the cloud?
Pardon me?
How resolved is the internal structure of the cloud in these simulations?
In this particular one, it wasn't that resolved, but we repeated it at 10 times. This was an SPH particle. We repeated it at 10 times more particles, and we got exactly the same result. And this is what we obtain every time we perform one of these simulations. And we are not the only ones to find it. There have been many studies looking at by Patrick and by Koyama and by other groups. And typically the result is you get supersonic motions, but not as strong as what you get in molecular clouds. Okay, so, but yet it does produce, the turbulence does produce nonlinear density fluctuations, which are still required by the model. Third, because the clouds are not in equilibrium, they contain infalling motions at all scales within them, and in particular, this means that you have accretion at all scales. So rather than considering the clouds in isolation, we need to consider the accretion from the upper level in the hierarchy of structures that we obtain. Collapse then starts at the largest scales in the clouds, and this is actually, it's a little bit against the standard idea that we have of inside-out collapse from Shu that we inherited, but actually this is the only way that collapse can occur, because collapse starts at the gene's length. Nothing smaller than the gene's length can collapse. So Shu only got an inside-out collapse because his initial condition was a singular isothermal sphere that had bypassed all the development of the central singularity. But when you do it from early stages, you get that the collapse proceeds from the outside in, and Ivo Stryker has found similar results. As the collapse proceeds, the fluctuations, the mass in the turbulent fluctuations decreases, and because of that, next you will have smaller collapsing regions, and but even though, so they start collapsing later, but they can finish their collapse earlier, okay? And because the clouds contain a large number of Jeans masses, the collapse is nearly pressureless, amplifying anisotropies, and this leads to an amplification of the anisotropies, because this result from the 60s showed that the collapse of an anisotropic pressureless sphere proceeds fastest along the shortest dimension. And so this is consistent with the formation of filaments, in which, I don't know if you can see them, but the material is falling into the filament and then proceeding along the filaments into the dense, the hub here. Yeah, I'll be done soon. And there's a hub, but there's secondary formation here. And this is contrary to the inertial inflow scenario that Padawan suggested, where that involved no gravity. And final thing is that the Larson line width relation here is not assumed to be a manifestation of the turbulence. It's assumed to be a manifestation of energy equipartition, but it's not virial balance. It's freefall, because it turns out that freefall is consistent with alpha equals 2, which observationally is almost indistinguishable from alpha equals 1 because of the uncertainties. And you can see that there's evidence from local galaxies that the virial parameter is around equals 2. And with this, well, I can skip this, which was the other part. And then this is a summary that, that compares the properties. And, but I'll leave it up for, and it's in the presentation so that you can look at it and have a nice handy table. And the only thing I wanted to say to finish is that we seem to be converging to the sense, in the sense that we have turbulence that is indeed driven into the molecular clouds. But the main factory of molecular clouds is probably, at least in Milky Way type galaxies, is the spiral arms, pulling in the gas, forming a molecular gas, then the molecular gas forms stars, and then it begins to be distorted by the clouds. But then you have something like, we have this pinball model for the clouds, in which basically you have a piece of gas trying to fall in, but it gets kicked out by some feedback, but eventually it wants to keep falling. And this is essentially what you have, and you have an increasing importance of the gravity as you go to higher and higher density, and that's it. Thank you very much.